Olá pessoal, aqui é o Ricardo Kerr, eu sou vice-presidente de relacionamento da ABS e nesse ano que estamos comemorando 30 anos de fundação da ABS, nós vamos trazer mais um podcast. Esta vez esse podcast é com o Lucas Jurecek, que ele é formado em 2017 pela Universidade de Tecnologia de Breno como engenheiro de pontes, com foco em estruturas protendidas. Em 2022, ele concluiu a Faculdade de Engenharia Mecânica de Ostrava, com especialização em mecânica aplicada. Tem 8 anos de experiência como engenheiro de produto no IDEA, estática, e é especializado em treinamento e suporte ao cliente. Eu vou passar a palavra para o Lucas, ele vai fazer sua apresentação e depois a gente bate um papo. Lucas, go ahead.
Thank you, Ricardo, for the introduction. Just few words. We are very happy that we can be again here in sunny Sao Paulo with Julio and my colleague here. And I would like to introduce you what we have from the point of view of the idea Statica for concrete design. But we will be focusing more on the theory, use cases, and the real-time showcases. So let me start. It was a very pleasure to meet you here. So let's go to the presentation and introduce you our solution that is called compatible stress field method. Regarding the agenda, I would like to introduce you the CSFM method, the theory that is behind, because it's very essential for every structural engineer to know the theory that is behind. Also the verification and validation and cooperation with the universities. It's also very essential for every finite element solution, I would say. And mainly the use cases on the real structures, case studies. This is the goal, what we would like to introduce you here. I would like to start with the really simple frame, because in every structure we can split on the so-called like a B and the D regions. The B, these are the yellow one. These are the regions where basically the Bernoulli-Navier hypothesis is valid. There is like a linear stress and strain relationship. But what about the discontinuity regions? As you can see on the very simple frame, these are like frame corners or the areas where are some concentrated loads or some openings, maybe the footings. This is also the areas where you need to use like a different approach for design. And you need to be very careful, because these are like a tricky regions on the structures, and if it's going to fail, mainly the whole structure is going to fail. So that's very important to have a proper design and understand that properly. I'm sure that a lot of engineers, like many engineers, knows the Stratton tie. Stratton tie is a essential theory that on the school everybody or every lecture for concrete design is a little bit touching this Stratton tie. A lot of theories in the Eurocodes are coming from the Stratton tie. So that's very essential and important theory that is working for ultimate limit states perfectly. Lower bound theorem. But this method suffering some limitations. Let's say you cannot calculate cracks. You cannot calculate the nonlinear deflections of these details. You cannot calculate the stress limitations. So this is maybe the problem that the method that I would like to introduce, the compatible stress field method, can cover. What is it? This definition, what you can see, this is the definition from the book, but that I will show you later. It's basically the nonlinear method for computer-aided stress field design. It sounds really like a scientifically, but it's pretty easy. It's based on the finite element approach, like a discretization of the continuum and you can calculate the stress and the strains based on the finite element solution. So this is the goal. And if you are using finite element structures, you are not limited by shape. You can design basically everything what you want. Something what is regarding the theory. For the solution, we consider the model that is based on the plane stress. So it means that the stress perpendicular to the plane is completely zero, or is considered as a zero. So here, in this case, we can say that sigma y actually is zero. So this tensor of the stresses that you can see here, tau xz, sigma z, sigma x, and tau xz, are considered for the calculations. But you know, for CSFM, because it's a design tool, so we need to be in compliant with the code, because every structure engineers need to follow the code, because it's important. So we our model is basically like neglecting the concrete in the tension at all. These are another assumptions, but before I touch these assumptions of the method itself, let me introduce you the model that is basically behind, because this is like a advanced model that you can use, or we are using. So there is the element of the concrete that is modeled like a wall. Basically, it's a wall element, and you are also inserting inside the model like a physically reinforcement. There are real reinforcement rebars. These are like 1D elements that can transfer only tension and the compression, no shear. This is this is the essential assumption. And the rebars and the mesh of the concrete element is connected via these purple elements, and these are, we call it like a bond elements. You know that the shear transfer between the reinforcement rebars and the concrete is basically transferred via these multi-point constraints and the bond element together in the very proximity of the element itself. And something what I would like to emphasize is that every reinforcement rebars in the real life has some anchorage shape, like a hook, loop. It's normal, it's standard on the structures, that like a reducing of anchorage length, basically. So I would like to touch only the main assumptions that every structure engineer should know about this compatible stress field method. Of course, there is like a more theory that you can like a deep dive inside and read out about it. But these are some like 6 or 7 points are very essential. The method is code compliant. I mentioned we are not trying to simulate reality. We are not trying to simulate that, because it's not the goal. The goal is to be in compliance with the code. The method that is used for cracks, for crack propagation, is based on it's called a smeared crack approach. It's not like a discrete modeling of the cracks like in the Athena or the other softwares. It's not like that. It's based on this smeared crack approach. The concrete in tension, as you can see in the diagram here, so the concrete in tension is completely neglected. What we consider is a concrete in the compression with consideration of some compression softening due to transverse tensile strain. Also, the reinforcement rebars has some effect that is called tension stiffening. I will continue later, or say more about it later. And also there are inside the bond elements that are basically representing the shear inside between the reinforcement rebars and the concrete. Just something about the material diagram of the concrete. We consider the material in nonlinear analysis, so this is the reason why we can use this parabolic rectangular diagram according to the Eurocode. According to the Brazilian code, because we are in the Brazil, so you are using a Brazilian code. So this material, you are also using the like a similar behavior of the concrete for ultimate limit state. Is it correct?
Correct.
Yeah?
We use the same code.
Mhm.
It looks like the European code.
Yeah.
The parabola rectangle distribution.
Mm-hmm. Yeah, I heard about it that your code is very similar to Eurocode. There
Yeah.
are only maybe some small changes in some parameters that if you change it, you basically create a Brazilian code. So that's perfect. It's perfect. Um, because it doesn't matter if you are in the Europe or in the Brazil, the physics works same. Yeah, so that's pretty cool. So regarding the concrete in the compression, we consider this green line. And as you can see, the green line is represented by this Kc factor. What does it mean? It means that due to transverse tensile strain, the concrete is basically softened. There is some compression softening because, if you compress something, there are some transverse tensile strain and the concrete cannot cover the tension. So it's like going to be some cracks and it's like a more soft. And this is representing in this diagram. So this is the reason why we have it there, and it's more according to the reality than if you consider this like a black line without the compression softening. What about the bond model? I was mentioning that between the reinforcement rebars and also the concrete, there are some elements that are representing the interaction between the reinforcement rebars and the concrete. And as you can see, the real behavior or real bond is represented by this dashed line. We consider, according to the Eurocode, the FBD, it's a bond stress, the bond strength, design bond strength, and really long plastic branch. So we can call that this diagram is perfectly rigidly plastic. What we consider, and it's really on the safe side and gives you safe results. If we are talking about the reinforcement rebars, so the rebars, there is a rebar and there is also concrete around the rebars. So you need to basically consider some interaction of the concrete and the rebars in between the cracks. And there is the effect that is very well known in the Eurocode and also the other code. It's a tension stiffening. If we are talking about the reinforcement rebars and the concrete, and this tension stiffening effect is basically doing one thing. He's not reducing the strength or do not affecting the strength, but he's affecting the ductility. So this is the reason why we have for reinforced concrete lower deflections. If you have higher amount of the reinforcement, there are like lower deflections. So this is the effect that is represented in this diagram. I was mentioning that we have this method has a benefit versus the Stratton tie, and the benefit is in the serviceability limit state. We can calculate cracks. We can calculate the nonlinear deflections, or the method can calculate basically the deflections. For calculation of the deflections, we are using basically two approaches, two methods. On the left side, there is the representation for standardly reinforced concrete. If you have a beam, there are some stirrups and longitudinal rebars. This material diagram or this mechanical behavior of the reinforcement rebars in between the cracks looks like that. But if you can consider that your like basically concrete block or some model can be lowly or that there can be very low amount of the reinforcement. So the behavior, what is happening in between the cracks, starting to be completely different, and you need to use like a different methodology or different approach, and this is represented on the right side of the screen. So two different approaches that are activated automatically because the method recognized the amount of the reinforcement inside the beam or wall. So that's really profitable for structural engineers. And if you calculate the cracks, so the calculation of the cracks, if we take it like from the really mathematical point of view, this is some integral over some band strip, I would say, and you will receive this VW, and using the transformation you will receive the real crack width that is W. I was talking mainly about the assumption for reinforced concrete, but we can, or the method is also accounting the pre-stressing. So I have maybe the question, how many buildings or bridges is pre-stressed in the Brazil or Sao Paulo? Is it many, or yeah?
Many.
Yeah?
Many.
You are using?
Yeah, we use for bridges. We use a lot.
Mm-hmm.
For buildings, more in the north part of the country, we have more buildings with pre-stressed slabs. Not here in the south part.
Yeah.
We are more conservative.
Mm-hmm. Yeah, of course. It helps reduce the thickness of the slab.
Yes, and
Yeah,
people.
and overcome the bigger span.
Yeah.
Yeah, that's. We also have a same experience in the Czech Republic, that a lot of structure is mainly reinforced, and for a bridge engineering, the structures are pre-stressed. All the structures bridges are pre-stressed because it helps to overcome big spans and reduce the thickness of the section and everything.
Yeah.
So that's really important for the design. So this is also the reason why we or in Idea Statica or in this compatible stress field method, there is considered the pre-tangent and the post-tangent tendons that you can very easily apply to your model and have a pre-stressed structures. I will touch the use cases where you will see, or everybody will see, the use cases from the real life, what we designed using this method. So this is, from my perspective, very important findings, that the concrete is working over the time. This is the model at in the 7 days has a different properties at the end of the design working life. So in the 50 years there is a different properties of the concrete than in the 7 days, and you need to somehow consider that during the analysis or during the construction stages of the structure, basically. For permanent, I'm talking mainly about the permanent load cases, because the permanent load cases are affecting the structure from the point of view of the creep and the shrinkage on the structures. And there are many methods that you can use. You can use a proper time-dependent analysis, but you can also use this effective modulus approach that is very well known, where you consider this phi. It's a creep coefficient that based on the creep coefficient you are reducing the modulus of the elasticity, because in the creep coefficient there is a hidden the time of the structure. So that's considered for CSFM, because there are some steps of the analysis where you apply at first. If you have a pre-stressed structures, there is a pre-stressing plus self-weight and some additional permanent load and some additional variable load after that. So this is something like a quasi-construction stage analysis that is inside. And we are approaching to the results, because I was talking mainly about the theory, but the results is something what the engineers need to know. The graphical scene or graphical outputs are very important for structural engineer to know what is the stresses, what are the stresses in the rebars, what are the cracks. So these are the outputs what you will receive from the solution, and there are ultimate limit state and serviceability limit state code checks. I think this is my point of view, that the software without verification and validation shouldn't or doesn't have a proper space in between the engineers, because you need to know that your software and outputs give you the correct result based on some verifications, validation with the real results. And this is what we have, because a lot of like structures and structural details are tested in the labs, and we have also the data, like the load deformation curve, and we can compare if our solution is or gives you some reasonable range of the results, and you are on the safe side or you are not on the safe side. So the verification is held by the Professor Kaufmann and his team in the Switzerland. So there is like they are doing a macro scale testing on the real projects or real beams, real walls with this like big dimensions, and based on that, we the data that are coming from the verification, we correlate the method based on that to have a proper results based on the experiments. Also some in-house verification, like a comparison with the other commercial softwares like Abacus, ANSYS, Athena. So we have also the comparison. And this is one of the experiments that I can expose. As you can see, this is the load deformation curve for depth end, and how it's been like or the failure mode that happened. Also the cracks. I think the science behind the cracks is very attractive, but very hard to understand, because concrete is like changing the material properties in every part of the structure. So it's not like homogeneous like a steel, for example. There can be some cavern or some stones inside, so it's changing the properties a lot. So the correlation in between the cracks, as you can see with comparison with the commercial software Athena, what we had, I think it's quite good. And this is the book. This is the book that everything or all the verifications, all the theory is published, and everybody can buy the book on the Amazon and read out the results from structural engineering field for discontinuity regions. And yeah, I will touch the use cases, because this is from my perspective, the most important part for structural engineers to know what they can calculate with this method, or what are the limitations of the method, and so on. These are some typical use cases for like walls and the panels. So you can very easily calculate the complex walls, some coupling beams, wall-on piles. So there is a question: if in the Brazil you have also have some experience with the coupling beams, is it like a seismic region here, or
No.
no?
We have very little seismic action. We have something, but very little on the north part of the country. Structures in São Paulo are not calculated with to support earthquakes.
Yeah.
But we have a lot of architects with great ideas, and we have a lot of walls and columns with holes, and
We're like architectural buildings. Very so many openings.
Yes, these openings
and difficult shapes.
Yeah,
exactly. Okay. What about if you are designing the beams? So you have some like a standard regions, but if you are designing the depth ends or deep beams, this is completely discontinuity region, and you need to use basically a strut and tie. Structural engineers are using strut and tie as a first option. I know that from the data what we have, that a lot of users is using strut and tie. If you are also designing the pre-stress structure, I was mentioning that the method is very suitable for pre-stress structures, pre-stress beams, and also the frame corners. you can design just the part of the structures, very small details, but you can design like a whole beams with the openings. That's very important. You are not limited by the like length of the structure, so you can design basically everything what is loaded in the plane. We were talking like a couple minutes ago about the bridge engineers, about the bridges, and on the bridges there are like pier caps, there are some bridge deviators, diaphragms, maybe some piers. So this is also the discontinuity region that the structure engineers can somehow handle and need to design it properly. Otherwise, if something will damage, so the bridge is completely going down. So that's very important to design it properly. And these are some like real structures where the CSFM method has been used or can be used. Some walls and the panels where between the transition of the column to the wall we can expect some like cracks, and you need to somehow consider it during your design. Some walls and the panels. This is like a use case from the Netherlands, where they are prefabricated structures. This is like a Lego, so you're assembling the structure very easily. And beams, pre-stressed beams, some depth end beams, and bridge engineers, some pier caps, pile caps, and bridge diaphragms that can be designed. And these are I have added some case studies from like around the world what structure engineers designed using DCSFM. I have one case study from Czech Republic, from the Brno, where it's reinforced concrete structure of the multifunctional building. The company is called Staticon, and they had like a really big trouble or some uncertainties regarding this frame corner. There is the like a junction of the slab, wall, and the other like a column, let's say. So the transition in between these three elements been really tricky, and they need to know what is happening there. So they used our software to validate if their assumptions are correct, and yeah, they were correct. Also some bridge from the Singapore, where they used the solution for bridge diaphragm. It's been heavily reinforced, and they would like to know if the amount of the reinforcement is sufficient, if the stresses are in the reasonable range, and also they needed to check like cracks. So they used that for design. In the London, there have been also some access ramps that in the interaction with the soil, because you were able to use some compression springs that are representing the soil, so you can simulate the interaction in between the soil and structure element, basically. And yeah, this is the airport terminal in Madrid, in Spain. So it's fantastic architectural structure, really like a curvy, and there are some piers that are phenomenal from the point of view of the design. There's like a steel to concrete connection here, and we are trying to simulate this discontinuity region, or basically this frame. Very easy to model it. And also some model from the Slovakia, where there's a combination of the steel and the concrete, and the anchoring of this steel structure to concrete wall, where there have been like a really big forces in the bolts or in the anchors, and the structure engineer had to somehow solve the connection in between the steel to concrete. The anchoring has to be somehow solved. So Ideastatica detail, or basically the CSFM method, has been used for the analysis and the code check. And actually, I would like to show you how easily you can work with CSFM method. So I will jump to the application and just very swiftly introduce the CSFM method, how the structural engineers can use it for daily praxis or daily basis. I would like to design the corbel, so I think it's like a standard prefabricated structure, corbel design. So as I mentioned, the corbel is reinforced with real reinforcement inside the structure. You as a structure engineer can check how many reinforcement rebars is inside, what is the anchorage length of the rebars. And if I go to the check, because we are running out of the time a little bit, so from the point of view of the code checks, you will receive as first the summary overview of all results that will tell you if all the entities in the model, like rebars, concrete, are okay. And as you can see, here are the green ticks that will represent that ultimate limit state and serviceable limit states are perfectly okay. And if you would like to know more what is happening, you will go to the detailed results. So in the strength, if I turn off the reinforcement rebars and turn on the mesh, so you can see that the stress under compression is like a critical here. I think at first I should display the deformation. So this is my deformation. So I can expect that this corner will be like a critical from the point of view of the compression, and it is. If I compare it or introduce the principal stress under compression, here is the maximum value, about the 20 megapascal. What about the reinforcement rebars? If you would like to know what is happening with the regarding the reinforcement rebars, the maximal stress under tension we can expect in this corner, because it's bended. Yeah. So there is like a combination of the shear and the bending moment. So this area is very critical, and also some like a crack can happen. So as you can see, 454 megapascal. So we are still, I think we are on the plasticity of the steel or rebars. If I will go to the stress limitations, I was mentioning that we can calculate the short-term and long-term behavior of the concrete. As you can see here, you can see the stress for characteristic combination in the 28th day. It's minus 10.4 megapascal, but you can also check what is happening in the 50 years. And the 50 years are represented by the creep factor that is written here, as the default value is 2.5. And you as a user, you can rewrite it based on your calculation. So if I come back to the check, so I can also display the short-term and the long-term effect. As you can see, the stress has been reduced, but more stress went to reinforcement rebars. What about the cracks? I was mentioning that we are considering the smeared crack approach, and the method that is inside is like a rotating cracks simulation, and the crack width is 0.39. So we are under the limit that is 0.4. We don't have nothing, or we don't have like a national annexes, so you as a user can set up your own crack width limit. So that's very handy. And the deflections, deformed shape, you can turn on the short-term deflection, long-term deflection, and the total deflection with consideration of the variable load cases. Everything is summarized in the report, because report is very important for every structural engineer to present it. And as you can see, you can export it to the Word and the PDF. All the model is introduced here. Also the loads combinations, boundary conditions, some scheme of the reinforcement, how many reinforcement is inside, and all the checks we went through are presented here. Of course, you can customize and turn off the results what you don't want. It's up to you, but here is basically everything. So this is the application, how it looks, and the method is implemented inside.
To start a calculation, you have to verify the structure, you have to design the bars you're using, and then your program verify the tensions.
Yes, me as a structural engineer, I will put some diameter of the rebars and run the calculation, and based on the diameter and the amount of the reinforcement, I know what is the stresses. So there is nothing like a predefined tools that will tells you, hey, there will be like two rebars with diameter 20 millimeters. No, you as a structural engineer, you need to put there something, and based on the calculation, you will know the stress on the rebars and how the structure behaves.
Okay.
Yeah.
The good old system, you try and verify,
Yes.
and verify.
Yeah, but it's very quick. The analysis is completely materially nonlinear. But if I start the analysis, so in 10 seconds you will see the results. Okay, and you have a result. So you can optimize it very quickly. So that's perfect for optimization
I see.
of your structure.
It doesn't give you alternatives.
No.
No,
No,
you have
no.
to do it on your own.
Yes,
All right.
exactly like this. Yeah, this is the mindset, but how we develop the application to, everybody engineer like put there what he think it should be there, and based on the experience, you have some very like a skillful guys that they know, hey, there will be like some amount of reinforcement, but you just only verify it if it works or not, and based on the results, you can see that, hey, I can reduce basically the diameter from 16 to 14 because here is some like a reserve or some space for optimization.
Mm-hmm.
You can do it very, very quickly. You will just click on the rebars and you will say that the stirrups or the rebars that is represented here won't be the diameter 14, but will be diameter 12, and you will just recalculate it. If you do it, so you will just run the calculation again, but I have a diameter 12, so maybe, as you can see, the results are not passing. So you need to put there 14 because it's not, otherwise it's not working.
Mm-hmm. I myself used to we're always very afraid about anchorage.
Mm-hmm.
So when I design, I put a bigger length of anchorage.
Yeah, the anchorage length.
Yeah.
Yeah. That's also covered here because here, as you can see, here is the anchorage check that will tells you if the rebars will be like pull it out from the concrete or not. So it's covered. So actually right now, if I come back here to my diameter 14 and run the simulation again, I will receive the passing results and also the passing anchorage check, and you will see what anchorage or what rebars is critical on this model. So if I will go to the anchorage, as you can see, the rebar here is critical.
Yes.
So here is the bond stress 3.1 megapascal. It's compared with the design bond stress, and you know that you're safe. You're safe. So that's very important to have like enough reinforcement rebars to capture the anchorage length.
Yeah. On a detail like this, I would go with this bar to the end of the column and turn down.
Yeah, that's like a experienced approach what you have. Yes, exactly.
We are all very afraid about this kind of structure.
Can imagine that there can happen something regarding this anchorage length. Great. So that's a great discussion. I'm very happy that I can sit here with you and have this conversation.
That's good.
Yeah. So if you have some question to.
Yeah. Can we use this? Here we have a lot of buildings that are made out of brick, structural masonry.
Masonry. Yeah.
Yeah.
Mm-hmm.
Can we use this thing for masonry?
That's very tricky question because masonry is like a completely different material than the concrete. There are some like a mortar and the bricks, and it's not like a suitable to design it with this tool. It should be designed with a different tool. Of course, you can bend the software, but you need to know what you are doing. But we highly don't recommend to calculate the masonry structures with this software.
We have also concrete panels, and then I had myself a case with a big wall, and the holes on the wall, they are not adjusted, and it was very difficult to calculate and to be safe. I had to bargain with the architect a lot.
Yeah, it's always.
Yeah.
I heard it always that structural engineers are like fighting with the architects, because they would like to have it like a really nice and shiny, but the static scheme is not working basically.
Yeah. We are very proud of our Brazilian code. Back in 1940, the concrete code, Brazilian concrete code, was the most advanced in the world.
Interesting.
And now our code is similar to European code.
Yeah, we have our simulation can be used for Eurocode or the ACI. You can select, but that's pretty easy to create your own code, because if I show you here in the settings, you can check here are the chapters in the code, 2, 3, 5, 7, 8. And as you can see, to create your Brazilian code, you need to change just 3 parameters for chapter 2, 2 parameters, and I think these parameters will be same for
the first
for Brazilian.
one.
The gamma C is for concrete, gamma S is for steel, 1.15.
We have 1.4 here.
For concrete.
Yeah.
So you will just type here 1.4, and
We
you
are
will
in
save
Brazil.
it. You will save it, and you have Brazilian code.
You have a Brazilian visa.
Yes, Brazilian visa, exactly. And here is like more chapters. Chapter 5 is for pre-tensioning, but again, like only 4 parameters. You change it, you save it, and you have your own code. Also for chapter 7, that is regarding the stress limitations. Here is the condition for characteristic combination 0.6, maybe you have 0.7, 0.5, but you will very easily change it, because I think the equations behind are the same for like the conditions. So that's, you can customize it. We don't want to like limit nobody, any country, to like create your or the country code what they support, because it's pretty easy to do it here.
I see. Comparando o CSFM com o sistema de bielas e tirantes, quais são as diferenças, o que é parecido, quais são as vantagens?
So in the strut and tie, the big benefit of the CSFM is that the method can calculate serviceability limit state, cracks, deflections, and stress limitation. This is something what the method like a strut and tie can't do it, because it's not possible. This method wasn't developed for this purpose. But if you compare the CSFM and the strut and tie, like every engineers or every university was trying to do that, to know what is the range and where we are in the comparison with the standard approaches. And you have some assumption like in the strut and tie, but here you exactly know what is happening on every element in every part of the like a structure, and all the reinforcement matters inside the concrete. But if you are considering the strut and tie, you just designing the struts and the ties, but there is also some like additional reinforcement that you do not consider, but it's working inside the mass of the concrete somehow, and this is considered here, so you will save like material and also the money. This is very important for structural engineer.
And when you're talking about precast beams, do you calculate the deformation with the cracked beam?
Yes, exactly. After the cracks, if the stiffness is like or the model is cracked, the stiffness is changed, so the deflections are higher. So it's represented here in the deflection. So if you compare the solution with reinforcement that looks like this and the elastic behavior, you will get completely different results, because this is the consideration of the like a change of the stiffness after the cracks.
After cracks.
After the cracks, yes.
And talking about beans, and you, if you if you calculate the cracked bean with your software and with other software, do you have more conservative calculations, or more your calculations are more close to the real
behavior?
Yeah.
Yeah, we have a comparison with our own solution based on the beam theory. That the comparison there, we also consider the nonlinear deformations with consideration of the a crack section, and we can say that this approach is more close to the reality. It's more close to reality because it's more precise like a model. But I was mentioning that we are not trying to simulate the reality, but if you insert here to the settings characteristic values and not with a design values, so you're really close to the reality basically, but not over the reality. You are like a 10%, 10-15% maximally under the real experiments. You have to experiment, so we know that the limits is something 10-15% max. So that's really good message. It's a great message for structural engineers, that you're always under, but not so far from the threshold. So that's very important.
I see.
Yeah.
Bom, nosso tempo está terminando. Foi um prazer estar conversando aqui com o Lucas. Além de ser muito simpático, ele trouxe novidades muito importantes para a nossa área. A gente a nossa profissão está sempre a gente tem que sempre estar estudando e vendo as novidades que aparecem. O cálculo de estruturas fissuradas com precisão é um avanço muito importante. Lucas, it was great being with you and knowing your CSFM design software, and I hope we can meet many times, and I hope you enjoy your stay here in São Paulo.
Yeah, for a couple of days I will stay here. So thank you for the opportunity to be here with you. It was a pleasure to meet you and have this podcast with you. So thank you so much. Also you and Julio and BIMWorks.
Thank you.
Yeah, thank you so much.